All right, guys, for your central question, it says, how do we apply Rolle's theorem and the mean value theorem? So two more theorems that you got to add to your tool belt of calculus knowledge. Okay, let's start off with Rolle's theorem. And let's just jump right into it. Basically, what Rolle's theorem says is that if you have a function that satisfies the following three statements, okay, so you got to show that all three statements are true. One, that the function is continuous on the closed interval AB, that the function is differentiable on the open interval AB, and also that f of A is equal to f of B. In other words, the starting value is equal to the ending value. That's crucial. That if those three statements are met, then Rolle's theorem says then there has to be a number C in that interval such that the derivative at C is 0. In other words, there must be at least one critical number between those endpoints. So let's look at a geometrical version of that. So let's say you have a function. Notice it is continuous on the interval AB. It is differentiable on the interval AB. And then also notice that f of A is equal to f of B, right? They start and end at the same y value. What Rolle's theorem says is that if those three statements are true, then there has to be at least one critical point or one critical number on there. Now, let's just think about this from a real-life point of view. If you're driving a vehicle, if you start at a certain location in your vehicle, and then you drive, but then you end up at the exact same point that you started at, you had to reverse direction at some point. Because if you think about it, if you were driving, and then you start driving, you start at this point, and then you start driving, but then you end up back at the same point you started at, you obviously had to reverse direction. For example, I'm driving this way, then I have to reverse direction in order to get back to where I started from. That's what this Rolle's theorem is talking about, okay? So that's your first theorem. An example would be, let's talk about why each one of these functions cannot be applied using Rolle's theorem. For example, this first function, even though it is continuous on the interval 0 to 4, it's not differentiable at this point. It's not differentiable at 2. Well, why do you say that? Well, the derivative to the left is negative. The derivative to the right is positive. In order for the derivative to exist, the derivative has to be the same on the left and the right. So the derivative does not exist at 2. So therefore, this does not meet all three of Rolle's conditions. The second one, you should probably see right off bat, the function is not continuous. There are gaps in the function at this value and at this value. So this function is not continuous, so it doesn't pass Rolle's conditional statement. So can't use Rolle's theorem. The three conditions that have to be met is it has to be a continuous function, has to be differentiable, and it also, the starting value has to equal the ending value. Okay. All right, the mean value theorem, let's talk about it geometrically. Basically what the mean value theorem says is that if you have a continuous function that's also differentiable, if you have this function and are looking at the interval A and B, then basically what it's saying is that if you were to calculate the secant or the slope of the secant line between those two endpoints on that interval, then there has to exist some point on that interval such that the derivative at that point, or the slope of the tangent line, is equal to the slope of the secant line. So visually, that's what this is showing. All right, now the MVT doesn't say where it is, but it does say that there has to be at least one point that exists. Notice that the formula for the secant line, of the slope of the secant line, would be f of b, because that's y, minus f of a, which is y, over b minus a, because that would be the x minus the x. Okay, and so like what I've just repeat myself, basically the mean value theorem says that the slope of the line tangent to the graph at the point x is equal to c is equal to the slope of the line segment. Okay, now that's just a geometrical interpretation of the mean value theorem. So let's just look at what the mean value theorem is. All right, so two conditions for the mean value theorem. The first thing is that it's got to be continuous on the interval, closed interval AB, It has to be differentiable on the open interval AB. If those two conditions are met, then the mean value theorem guarantees that there is some point C between the interval AB such that when you take the slope of the segment line between A and B, it's equal to the derivative of the function at that point. Okay, and so that's what this is saying. The derivative must equal the slope between the endpoints for at least one value of x. Now, a good example of this is like, for example, if I was driving from Climax to Cairo, let's say that my average speed limit, my average miles per speed that I was going from Climax to Cairo was 60 miles per hour. Now, that doesn't mean I'm going 60 miles per hour the entire trip. For example, I know I'm not going to go 60 miles per hour in Wiggum, because if I try and go 60 miles per hour in Wiggum, I'm obviously going to get pulled over and get a ticket. But when I say I drive 60 miles per hour on average from Climax to Cairo, that means that I was driving a little bit faster in some places, driving a little bit slower in some places. But at some point on my trip, I was driving 60 miles per hour at some point between Climax and Cairo. And so that's what this is saying. It says if a car travels smoothly down a straight level road with average velocity of 60 miles per hour, we would expect the speedometer reading to be exactly 60 miles per hour at least once during the trip.